way of looking at a very broad range of concentrations. And so here are my data that for 3 compounds it takes, interpreting this at a layman's level, comparing red to blue, it takes less of the blue at any given concentration to have the same effect. So if we're looking at, let's look at about 80%. We get about 80% of the cytopathic effect, so we've inhibited 20% at about 10 units of concentration. To get a similar effect, we have to go out to 2 point something on compound B, and that's more than a tenfold change in inhibitory effectiveness. And so, of course, if you add an infinite amount of the drug at some point, you're approaching an asymptote here at 0. So you can fit these data in the simple case to a simple model. Y, so this is the inhibitory percent inhibition, is where it starts, or in a general sense this would be called the span, because in reality you don't get data that start at 100 and go to 0. You might get data that start at 80 and go to 20. So what you're looking at is that array. In my simulation it just happens to be 100. So the span over 1 plus 10 to the, so this is a decay x, so that's our concentration, minus log EC50. Importantly, x is really the log of the compound's concentration. You can express this equation a lot of different ways to derive it. There's at least one pharmacology class. So right now let's just think about, sorry, not EC50, IC50. So let's think about what IC50 means. So IC50 is the drug concentration at which we achieve a 50% inhibitory effect. There's no reason why it has to be IC50, but it could be IC20, it could be IC30. People just like to think in 50 because that's a good, you can see halfway, right? So our IC50s are going to be wherever our data cross that 50% inhibition threshold. So our IC50 for blue is right there. Our IC50 for red is right there. So when x equals IC50, then the log of x is going to be log of IC50. That's going to be 10 to the 0 or 1. So that's 100 over 1 plus 1, or 100 over 2, which is 50. So the IC50, to measuring inhibition and describing it with fits to this equation, give you a value that tells you something that is very useful in comparing it to other things. So let me see if I can illustrate that. So what I've done here is created a simulation to fit the data. So we have 3 different compounds here. So you have the red compound, and this is fake experimental data. If you saw data this good in reality, you'd know I cheated. And then the blue is for compound A, and then the green is for compound C. What's the best drug? Green? C. And somebody other than Drew, describe why it's C.
You need a low dose.
I'm sorry?
Is your IC50 at lower concentration?
It takes less of a dose to get the effect you want, and it takes less of a dose to get the near maximal effect. None of these are ever actually zero, as you'll see. So you know that, but as a chemist, you might want to take these data, get a quantitative value, and then decide to make a change that we can then compare. So I've taken the same log scales. I could do more points, but it would be a little more confusing. And then for a given value, this is compound A, compound B, compound C, calculated what inhibition, so look up here, what you would see is the XL, what you would see if one, if it were big enough, and two, if you could, if I hadn't highlighted it in black, what you see up there is the XL expression of that equation over there. So I've defined the value in this cell to be 100 divided by 1 plus 10 to the value in this cell. So that's the log of the concentration, so that's this axis. Minus the log of IC50, which I've defined as whatever the value in this well is. So what you can see, what you would see, is it's wrong. Right? So this value generates these data for any given concentration. So, and then it plots it out when you look at this switch out here. So there are 3 of them on the graph. So for an IC50 of 12, my blue data would look like this. What does that mean? The IC50 of the blue data is not 12. So when you get into grad school and you spend all your days and nights doing these experiments and you get the raw data, what you'll do is go on the graphic program and say fifth, and it will do this for you and you won't have to think about it. But let's say 100. Oh, that's too big. Try 50. Oh, that's getting there. 30. Getting worse. 35. Oh, that's probably about good. So for an IC50 of 37, whatever these units are, let's say nanograms per microliter, I get a simulation that goes through my clothes. So the IC50 for compound A in this assay is 37. Let's think about B. It's not going to be 5. I've got the red curve there. Doesn't fit the data. I know it's going to be more than 37. Because 37 generates this curve. I want to generate that curve. So let's try 50. That's too much. 100. Oops. So, too little. Crazy. 500, still low. 575. So there are 2 IC50s that fit the data. What does that tell us? It tells us that compound B, it takes the inhibitory concentration of 575 nanograms per milliliter, whatever my unit is, gives us a simulation that fit the data. Therefore, we know that it takes a lot more, over 10 times, about 15 times, the concentration of the drug to get the same effect upon killing our viruses. Therefore, given these data, there are other variables here. Compound A is a better drug than compound B. We know C is going to be better than A. Let's try it. 1. Nope. So there I've quantitatively fit in an iterative fashion, much slower than a computer, experimental data that have given me a value that I can use to understand differences among these compounds in this assay. Now, I generated the data by doing this. I cheated because I did the simulations first, and then I went and pasted them in the data, and then I erased my IC50 so that I could do this exercise with you. But you're going to see data in your text. You're going to see data in papers that look like this. And now, I know how to interpret it. The further out the curve, the weaker, the worse the drug is at causing the effect. We talk about things in terms of IC50 because we don't know that the binding causes the effect. There are multiple variables involved here. It might be the binding causes the effect, but the drug has to get across the cell barrier, and its ability to do that may be more important than its affinity for the molecule. So there are confounding variables, and they're variables that we don't know exist when you're dealing with a drug development. And so you have to talk about things in terms of IC50 rather than affinity constants because of those unknowns. I'll put this up on E2L for anybody who wants to play around. So in answer to an earlier question, how do you get a drug that causes a side effect? Well, you don't, unless you invent the perfect drug. Generally, you shouldn't take drugs if you don't need to. We talk about safety in terms of a selectivity index, or SI, and it's equal to some measure of host toxicity over its antiviral activity. Again, it's a matter of unit definition, but one way to express a selectivity index would be LD50 over IC50. So LD50 is that dose that's going to kill 50% of the test subjects. A high LD50 is a good thing. It may be a little counterintuitive. For an LD50, you want to have to add a lot to kill somebody. So a high LD50 is a good thing. Water's LD50 is ginormous. A low IC50 is a good thing. So for selectivity index, high equals good, low equals bad. The table in your text is not available, so this is a slide. I'm getting some furrowed eyebrows. So let me just say it again. If you don't get it, we'll continue exploring it. LD50 is the concentration of the drug at which 50% of the experimental subjects die. It's by no means the only measure of toxicity. You could look at some marker of liver damage, for example, in terms of acetaminophen, but in terms of easy to measure outcomes of an experiment, death is one of them. Oh, 5 of the 10 mice are dead. That must be the LD50.
The lower it is, the faster it kills.
Right. So the lower the LD50, the less of a dose it takes to kill. So in terms of drugs, you don't want to kill the patient. So if you had an antiviral that had a LD50 lower than its IC50, well, that would be a lawyer's dream in terms of suing the drug company. It kills more subjects than it cures. They're not directly comparable. So you look, the higher the LD50, the better. And then the IC50, the lower that is, the better. The less of the drug it takes to cause an inhibitory effect. And so when we're talking about screening a bunch of different compounds for which is the better drug, one of the things you would look at is the right mix of low toxicity, high activity. And ideally, this is infinity and this is near zero. But real drugs don't work that way. So, going through the parade of antiviral drugs, we start with nucleoside analogs. How does a nucleoside differ from a nucleotide? I know. Here's a nucleoside. Go guanosine. How does that differ from guanosine, the nucleotide? No, phosphate group, that's it. We're gonna, so these drugs are gonna, since they're analogs, they're gonna be used to inhibit nucleotide synthesis. Or nucleic acid synthesis, sorry. And in the interest of time here, I'm not going to go through the examples in your text of for example, acyclovir, which inhibits DNA synthesis. They're just listed there. I don't particularly care. Well, I don't know. Maybe you should know what acyclovir is. But we'll take as our example azethymidzine, which is is a reverse transcriptase inhibitor. First approved, actually I don't know if it was the first approved, it was an early approved drug for HIV treatment. So what they are so azethymidzine is here. What you have is a analog of a nucleic acid. The way all of these drugs work is by binding the polymerase. In this case, this one is very specific for reverse transcriptase, and you've incorporated normally the 5' 3' centroids would go formation of phosphodiester bond at the 5' phosphate. This is a nucleoside, so it actually gets phosphorylated in the cell. But then if you look down at the 3' hydroxyl, it's not a hydroxyl at all, so it can't form a phosphodiester bond with the next one chain. So these are chain terminators when they're incorporated. When they're incorporated into a nucleic acid, they make it so that the nucleic acid can't be synthesized. A lot of anti-cancer drugs are also chain terminators, and that's because these drugs go after the replicating entities, whether it's a tumor cell or a virus. Your senescent cells are generally not in need of nucleotides, and they're not actively replicating. So replicated drugs. I'm trying to figure out how to get through this. Time left. I may spill over into Monday, which would not be bad, I guess. We have protease inhibitors. So many viral proteins are produced as polyproteins. Oh, I'm sorry, I forgot. There are also so these are the AZT, 3TC, other nucleoside analogs are at least based off of natural products, modified therefrom. This is a rationally designed molecule to bind to reverse transcriptase. A bunch of chemists said, oh, that'll fit, and it does. So it's a non-nucleoside inhibitor. So there are non-nucleoside inhibitors of reverse transcriptase. Trace inhibitors, for example, GAG and GAG-PAL have to be hydrolyzed. Have to have a peptide bond broken. If you have a molecule, so HIV protease inhibitor, there are different ones that are showing you ritonavir here. They look like polypeptides, but they aren't. And so you see what looks like a polypeptide backbone. This binds to the protease, and it has a bond in the active site that is not a peptide bond and thus can't be cleaved. So this is competitive inhibitor. There are attachment and fusion inhibitors. So for HIV, for example, we look at the GP120 interaction between host and virus. You can inhibit that with small molecules. You see detachment inhibitors. The anti-flu drugs, this is an example, such as Tamiflu, work that way. We talked about them earlier in the semester. There is an integrase inhibitor as well. So this would be or an inhibitor of provirus formation. I'm out of time. I'll pick up for about 5 minutes of this on Monday, and then move on to the penultimate chapter.
Is that
Penultimate.
PIO virus or pro virus?
P-R-O, sorry.
PO virus. PO virus.
So integrase is the enzyme